Welcome, I'm Nick Tillett. In this, the fourth of our series of 6 in-row training videos, I will explain how to set up our within-row guidance systems on a new machine before you get into the field. This presentation builds on information from our inter-row guidance videos. So, if you've not already done so, you might benefit from watching the equivalent inter-row video presentation first. In this presentation, we'll cover leveling and the special camera setup considerations for within-row operation. We'll also cover odometry. We've split the rest of the presentation into sections relating to different individual in-row treatment devices. Whilst you can mix multiple treatment device types on a single machine, it is likely that you are only using one. So feel free to skip to the specific in-row device that suits your interest. We start with rotor mechanical setup, along with how to select the optimal rotor disc to suit applications, as well as rotor setup and testing. We will go on to reciprocating blades and finally to spot spray nozzle testing. In general, treatment of individual plants requires more accurate camera alignment than inter-row operation. Many crops requiring individual plant treatment are grown on beds with variable depth wheelings, making it particularly desirable to automatically level the tool frame in relation to the bed top, and therefore maintain a consistent camera orientation. This is normally done by running 2 lightweight depth sensing wheels, one on each side of the machine. One or both of these may incorporate an odometer. The level of these wheels is sensed by 2 proximity sensors on each side. Alternatively, leveling sensor inputs can be performed by an ultrasound sensor on each side, providing up and down limit outputs, offering a non-ground contacting option. For the purposes of this video, we will assume the leveling inputs will be performed with a depth wheel arrangement. They are arranged so that neither is activated if the frame is too high. One being activated indicates an acceptable height, and both being activated indicates the frame is too low. Bidirectional valve outputs are activated on the basis of the position sensors to bring the frame into alignment. Adjustment is therefore done purely by the mechanical positioning of the sensors relative to the mechanism they are sensing. The further the 2 sensors are apart, the larger the deadband in level adjustment. Inter-row operations only require a sample of the rows within a plant about to be viewed. Within-row operation, on the other hand, requires every plant to be tracked individually. To achieve that, it is more likely to require multiple cameras, and those cameras may need to be fitted with a wider angle lens to achieve the required view. Furthermore, it is even more important to ensure machinery parts are kept out of the camera's field of view. For best performance, it is desirable that the final view of a plant is a near vertical one. This gives best separation between adjacent plants and forms a better basis for the assessment of crop plant size and position. Our dynamic tracking algorithms work best if 4 plants are visible in a single frame along each row, with an absolute minimum of 3. Once cameras have been positioned to view all of the crop rows, it is necessary to measure camera parameters and enter them into the relevant configuration. Pay particular attention to the look-ahead distance. The techniques for doing this are described in the inter-row training material. Settings for in-row are no different, but it is important that the distance of the cameras are ahead of the cultivators is measured accurately. Rotor position should be measured to the centre of rotation at soil level. Remember to make sure the implement and the cultivators are set at their normal working levels before taking any measurements. Precision in-row operation requires accurate odometry. To achieve that, you need large diameter odometer wheels to help cross rough ground smoothly. Mounting those wheels on a parallelogram frame ensures changes in level are not seen as changes in speed. You should not mount odometer wheels on a simple trailing arm, as this will give an apparent speed fluctuation as levels change. You have two options for sensors. For the first, it is acceptable to simply count wheel studs or spokes. Accuracy in this mode is perfectly adequate, but when starting, 2 studs must be passed before any speed measurement can be made. This can give a poor impression if regularly stopping and starting, during a demo, for example. The second option is to fit a full phase quadrature encoder that will give a near instantaneous precision speed measurement from the start. We will now discuss how to mount in-row rotors of either the hydraulically driven or electrically driven types. They should be mounted as close as possible behind the bottom of the camera field of view. This minimises the distance over which plants are being tracked by dead reckoning. For this reason, they're often mounted ahead of inter-row cultivators. To accommodate tighter row spacings, rotors can be staggered. Rotors should be tilted approximately 5 degrees to the vertical so that they cultivate slightly deeper when engaging between plants. There should also be a lateral offset from the crop row centerline. The size of that offset forms part of the disc part number, but will generally be either 4 or 6 centimeters. Lateral offset is measured at ground level as depicted in the diagram. Looking now from the side, rotors should be angled approximately 5 degrees forwards so as to minimize draft force. It can be helpful to integrate some sort of angle adjustment to the rotor mounting arrangement for easy in-field adjustment. Be aware that as rotor forward angle changes, it can change phase relationship between discs and plants. It is therefore convenient and less confusing to set all rotors to the same angle. Rotors are normally only required to do light cultivation at depths between 1 and 3 centimeters. However, a robust design can cope with deeper cultivation. Depth control and adjustment are best integrated into the mounting arrangement, keeping the wheel near the disc for accurate depth control. The floating design is desirable, enabling rotors to move up if being forced into the ground, and allowing them to climb over obstructions. A number of alternative disc profiles are available to suit different within the row plant spacings and to accommodate different uncultivated buffer zones around the plants. Each disc profile can be used on a wide range of crop geometries, but selecting the most appropriate disc for your range of crops will enhance performance. Swapping discs is an easy process involving 2 easily accessible bolts. Discs are defined by their part number, which are defined by these parameters. disc size, the offset, the disc type, and the plant zone. The disc size is defined as the plant-to-plant spacing at which the motor control will give a constant speed of rotation through each cycle given an even plant spacing. If actual plant spacing is greater than disc size, rotation will slow between plants. If actual plant spacing is less than disc size, rotation will speed up between plants. Speed of rotation will also vary with forward speed. For best performance, pick a disc size that is close to the average plant spacing, but no more than 10% greater than the minimum spacing measured in the field. The maximum forward speed of the implement can be determined by multiplying maximum rotor speed by the disc size. It follows then that for the best performance in terms of work rate and accuracy, you should select the largest disc size that meets these criteria. Though in practice, it is rarely necessary to run at maximum speed, and smaller compromised disc sizes can be used to suit a wider range of crops. Other disc parameters are disc offset, which is the lateral offset between the centre of rotation and the plant centre line, as described on an earlier slide. The disc type, typically denoted by a W or a T, describes whether the disc profile is optimized for weeding or thinning. And plant zone is the diameter of a circular area which is intentionally left uncultivated around the plants. So let's look at an example. We want to weed lettuce planted at a nominal 30 cm between plants within the row. We want to leave a 7 cm diameter uncultivated zone around the lettuce to avoid root damage. We have a choice of two standard discs. A 25-4W7 and a 29-4W7. If, on making actual measurements in the field, the minimum plant spacing was in practice 24 cm, then the 25-4W7 disc should be selected. If field measurements showed a more uniform spacing and the minimum spacing was 28 cm, then the 29-4W7 disc would be acceptable and would allow a slightly higher forward speed. Below are a selection of common disc sizes, the CAD profiles of which are available from Tillett and Hague, free of charge. As you can see, there are some instances with the two variants of a disc size with different plant zone parameters. Selection of an appropriate plant zone variant of a disc depends on the required area of cultivation and clearance around individual plants. So now we're going to talk specifically about setting up electrically driven rotors. Please consult the manual for instructions relating to the hydraulic equivalent or electric rotor machines built prior to 2023 that have a slightly different procedure based on setting dip switches. Start by going into the service menu and selecting Setup Rotors and entering the password. If rotors have already been identified, they will be listed here in order from lowest ID at the top of the screen to highest ID at the bottom. Green clockwise arrow indicates clockwise rotation and a red anti-clockwise. If no rotors have been assigned, none will be listed and the rotor LEDs will be off. Select Assign IDs to start the assignment process. Start allocating rotors from the left by pressing the button situated at the back of the leftmost rotor. The LED at the front of that rotor will turn red and that rotor will appear as rotor 0 as a line on the screen. Continue from along the machine left to right until all the rotor buttons have been pressed in sequence and a full set of rotors are listed on the screen. By default, rotors are set for clockwise rotation. If you touch on the arrow, it reverses direction and changes colour. To exit, touch the bottom right button and your electric rotors are now set up. We will now do the initial rotor startup test. Lift the implement and power the console up. Rotor power source should be turned on at this point. For electric rotors, turn on the 42 volt power. For hydraulic rotors, set maximum oil flow. From the home screen, select the in-row option, which prompts you to check that it is clear to do a rotor startup test. Once you have confirmed it is safe, all the rotors will spin up together, rising to a maximum of 4 revolutions per second, with the message synchronizing encoders displayed on the screen. If a startup test is successful, rotors should return to their parked position, as shown here, and the console will load into the working screen, ready for operation. If the initial rotor startup test is unsuccessful, messages to help diagnose rotor faults are displayed. They include no rotation, indicating that sensors did not detect rotation, indicating a possible sensor error, or rotor power supply failure. Reverse rotation, suggesting a possible wiring fault, or for hydraulic rotors, the hydraulic supply could be reversed. Comms fail indicates an internal communication fault has been detected. Turn the system off and check connections. An index sensor fault suggests a sensor that should be triggered once per revolution is not being triggered as expected. Run a rotor test and view the output graph to help with diagnosis. An encoder fault suggests the rotor speed sensor is not giving the expected smooth output, and a fault has been detected. Run a rotor test and view the output graph to help with diagnosis. Get rotor calibration advised. This message should only be displayed with hydraulic rotors. The full rotor test can be accessed from the Advanced Settings and Diagnostics page. To test rotors, ensure that their power source is on and select the Test Rotors utility. Select either a single or all rotors to be tested using the arrow keys and return buttons. If it is safe to do so, press Begin to start the test. The first rotor will start to rotate. A graph tracking expected rotor speed against actual rotor speed is displayed. A straight 1-to-1 graph with minimal noise indicates a good test. This process is repeated for each rotor in turn and has been speeded up here to save us time. Following a successful rotor test, an OK message will be returned. If there is a problem, diagnostic advice will be offered. Variability between individual hydraulic components necessitates calibration, which can be selected from the advanced setting and a diagnostic screen. As before, check the implement is lifted and the hydraulic supply is on. This time, select Rotor Calibration. Each rotor will ramp up in turn, starting from the left. The calibration test plots and records valve current against rotor speed output. This information is used to automatically calculate calibration parameters for each individual rotor. Calibration is affected by oil viscosity, so it's best done at a normal operating temperature. A smooth curve should be displayed without too much sensor noise, though a little hysteresis is to be expected. Once all rotors have run, you have the option to save these calibrations or restore defaults. The recommendation is to save successful calibrations. For help interpreting rotor calibration results, see the reference manual. The hydraulic flow test checks the hydraulic supply can produce a high enough flow rate to match the desired work rate. Ensure the hydraulics are set to maximum flow, raise tractor engine revs to a normal working level, and select the hydraulic test utility. Lift the implement and ensure all personnel are clear, and then press Begin. All the rotors will gradually increase in speed. If sufficient oil flow is available, they will reach maximum rotational speed of 4 revolutions per second. And rotor speed is displayed graphically. If rotor speed plateaus or supply pressure drops before the required speed, the hydraulic supply flow must be increased or forward speed reduced. If the tractor's own hydraulic system is supplying the oil, this will necessitate operating in a lower gear ratio. A rise in return pressure with increasing flow indicates a restriction in the return line. If the machine is equipped with reciprocating cultivators and a configuration file that includes those actuators is selected, you have the option to test their function from the System Information and Diagnostics menu. Test cultivators sequentially tests individual cultivator output channels for 1 second each, starting from left to right in mapped order. This test allows for checking of actuator function and mapped order. Test all cultivators activates alternate cultivator output channels for 1 second on and 1 second off. This test is useful to check for adequate flow capacity of hydraulic supply and adjustment of individual cultivator actuator flow to ensure even operation across the implement. If the machine is equipped with nozzles and the configuration file that includes those nozzles is selected, you have the option to test their function from the System's Information and Diagnostics menu. Select Test Nozzles to get these options. The first is a simple visual test in which all nozzles are turned on for 1 second in turn, starting from the left and going to the right. Flush Nozzles option activates alternate nozzles for 1 second, then turns on the other half in a continuous cycle. If spray pressure monitoring is fitted, further tests are available to check for leaks and blockages. We hope you found this presentation useful. Remember that it's the 4th of a series of 6 videos that you can select from our website and view them as many times as you want. Our website also has links to other reference and training material. If you have any questions, please get in touch. Thanks for watching.